Welcome to lesson 406, Prismoidal Rule. This is a tool we use for finding volumes, and it's a really nifty tool, and you use it for finding volumes for frusta. I knew I had to spell that. Frusta. What's a frusta? Well, the real question would be, what's a frustum? Frustum, singular, frusta, plural. A frustum is something like that. This looks like a cone that somebody kind of chopped the top off, right? That's exactly what we mean by frusta. And you can have a frusta of a cone, you can have a frusta of a pyramid, you can have frusta of various shapes. So the way this works is actually really cool. You want to find the volume of this thing. What you do is you first ask yourself, what's the area up top? I'm going to call it A sub 1. You also ask yourself, what's the area down here at the bottom? And that's going to be called actually area 3. The other thing you have to figure out, well, let's see, how can I draw this nicely? I'm going to try to do this. Something like this, right? So that's supposed to be halfway up. Maybe I'll write that here. Has to be halfway up. Has to be to get to here. But we'll call that A sub 2. So you've got the area of these 3 circles, top, bottom, and whatever's in the middle there, exactly halfway up. And the volume, it turns out, you take the height of this thing. So maybe I'll get this out of the way now. Just remember, A2 is supposed to be exactly halfway up. The height of this thing, of course, is just straight up from the table, so to speak, all the way up to the top. So anyway, the volume is, you take that height, you divide it by a 6, open up a big bracket. You take A1, you take 4 times A2, and then you take A3. That's the formula we're going to be using throughout this entire lesson. It might remind you, particularly this 4 thing in here. Remember when we did what was called Simpson's rule a few lessons back? We would take like an irregular area, we'd break it up into have to be an even number of strips, and then you would measure, like, this might be called Y1 and Y2 and Y3 and Y4 and Y5. Anyway, we had that formula that said the area was something, and it had like this Y1 plus Y5 plus 4 times the Y evens, and anyway, that 4, remember that 4? So if you see the 4 up here in this formula, you can say, I wonder if this has anything to do with Simpson's rule, and it turns out it has everything to do with Simpson's rule. It is, in fact, precisely Simpson's rule for volumes. It's another name for Prismoidal rule. It's the same thing. So let's see this in action. So here's a nice little Frusta of a cone right there. And I'm having a hard time scrolling that equation up because I like it so much. I don't want to make it go away, but okay. Let's do this example 1. Frusta of a cone. Biff has a frustum of a cone, a chopped off cone. And we got some dimensions here. The diameter across the bottom is, 12 centimeters. Okay, cool. The diameter at the top, so that's up here. The diameter is, 6 centimeters. Okay, cool. And the height of this thing is 10 centimeters. And that's all the dimensions we need. We can figure out the volume of this thing. Now, to get this going, let's see. Let's call this A sub 1. Now, it's a circle, so you can either use pi r squared, or since they gave us the diameter, I'm going to use pi d squared over 4. So I got pi, the diameter is 6, that's going to be squared over 4, equals, and did I push this button already? Oh, good. I got 28.274, and these would be square centimeters. So just hang on to that. That's A sub 1. Down here, we'll call this A sub 3. Remember, A sub 2 is going to be in the middle. So again, I'm going to do the old pi d squared over 4 thing. Plugging in d equals 12 centimeters this time, I end up with, what I get, 113.10 square centimeters. So I'm following my habit of always using 5 sig figs when I'm in a calculation. Now, the key question is, if I come halfway up this thing, what will be the diameter of that circle? I need to know its diameter so that I can find its area, right? Well, what is the diameter of this thing? What's your best guess? Did you say 9? If you said 9, that was right. How did I get 9? Well, we're taking advantage of the fact that this is a nice straight line that goes from here to here. So when you have straight lines, coming halfway up here, this dimension will be the average of this one and this one. So I can just go 6 plus 12 over 2, which is 18 over 2, which is 9. It's always going to work that way. As long as this is a straight edge, it's not a weird curvy edge like this or something. It's a nice straight edge. So as long as you have a nice straight edge, you can just take the average of this upper diameter, lower diameter. The average is 9 centimeters. I can use 9 centimeters in my formula here to get what I get. I got 63.617 centimeters squared. Cool. I got my 3 areas. Now I grab my formula. My formula says I should go h over 6. I should take area 1 plus 4 times area 2 plus area 3. This is why we're dividing by 6, by the way. We're taking sort of a weighted average of these areas. 1 times this area, 1 times this area, 4 times this area is basically, I've added up to 6. So I'm dividing by 6. So it's a weighted average is what's going on here. So anyway, get this out of the way, get this out of the way, get this out of the way. That looks much better. Okay, just plugging our info in. The h would be over here. That's our 10 centimeters. Put that over a 6. A sub 1 is the 28.274 square centimeters. And then we got 4 times area 2, which is the 63.617. And then we also add this area 3 at the bottom. And push buttons. And what did I get? I got 659. I'm still keeping 5 sig figs. 659.74. And this would be centimeters times centimeters squared. I'm going to now have centimeters cubed. It's a 3D object. You expect a cubed, right? Centimeters cubed. Some people would call these cc's, which means cubic centimeter. You could say cc's if you want. Actually, you know what? Really, you might as well know this little piece of trivia. A cc is the same as a milliliter, so you could say it's 660 milliliters if you wanted to, just for fun. So, yeah, that's it, right? I just got the volume. Now you have to admit it. That's got to be the coolest thing since ice cream, right? You wanted the volume of that cone? Just boom, boom. This nice little Simpson's rule type of thing gets it for you. And the good news is you can use it for more than just cones. You can use it for pyramids. You can use it for funky pyramids, like pyramids that have a hexagon on each, or a hexagonal cross section. So here's a sort of a pyramid, you might say, on its side. Technically it's a hexagonal prism. It has a length of 14 inches. Okay, I'll just kind of remember that somehow. That would be the length going this way, of course. Length of 14 inches. We're going to cast this. Cast aluminum? I don't know what we're going to cast it out of. So in order to cast this, we need to melt down some bar stock. The bar stock has a 1 by 2 inch cross section. Okay, we'll worry about the bar stock later. To figure out how much bar stock we're going to need, we're going to basically need to know, well, how much stuff is this? This thing is how much stuff. In other words, we need the volume. We need to find the volume of this thing. So need volume. Then we'll worry about the bar stock last. We need the volume so we know how much we need. So, okay. Looks like the hexagon has a 1 inch side on this end. Each side of the hexagon is 2.5 inches on this end. And of course, we're going to have to worry about a location halfway down here where, what do you suppose this distance is going to be? Well, since again, this is a nice sort of a straight line sides here, What did I just do? We can actually just take the average of the 1 and the 2.5. 1 plus 2.5 over 2. Turns out this is 1.75 inches across right here in the middle. So I got 1 inch there, I got 1.75 inch in the middle, I got 2.5 inch there. That's my dimensions. So my area here I'm going to call A1, my area here, and again I'm talking about the area of the cross section. So it's like if you could see the rest of this thing somehow, I'm talking about the area of that cross section halfway up. So anyway, A2, let's see now here, and then A1 will be this one. Now, how the heck are we supposed to find the area of a hexagon, I ask you? Well, I'm going to ask you to remember back to, I can't remember if this was lecture 401 or 402, but if we had an equilateral triangle, and that's not equilateral looking enough for me, so let's get maybe a better picture. That looks a, we're just going to have to go with it. If you have an equilateral triangle, remember what equilateral means. All angles are 60 degrees, right? If I know an equilateral triangle, there's a formula that we had. Equilateral basically means all sides are the same as well, so call that little a. The area of this cross section for an equilateral triangle is you take a squared and then you multiply it by this square root of 3 and you divide it by 4. You might remember that formula, or at least having a little deja vu or something with this formula, because we have seen it before. So if you have an equilateral triangle, that's how you would get the area. Why does that help us? Because a hexagon is made up out of 6 of these things put together. Right? That's what a hexagon is. It's 6 of these equilateral triangles. And notice the A would be, the dimension along the edge, like this is an A right here. So that means I can find, for example, A sub 1 by saying, well, I got 6 of these triangles, 6 of these equilateral triangles, and the area of each of those is going to be A squared, square root of 3 over 4, where A squared is the 2.50 squared, square root of 3 over 4. And when I punch the button on that, I get, let's see, what did I get? What did I get? I got 16.238 square inches. And then for area 2, maybe I'll just kind of jot the formula over here someplace. You're going to do the same thing. 6 times A squared, square root of 3 over 4. But you're going to use that the A is right here, 1.75. And punch a few buttons, you get 7.9566 square inches. A1, same formula, but you would use this for your little a. You'd put 1 inch right there. And I got an area here of 2.5981 square inches. Okay, cool. So now we can get the volume of this thing. What color do we want? How about purple? That looks cool. So the volume of this thing is, remember the Simpson's rule for volumes, which is also called the prismoidal rule. Take the height over 6, multiply it by area 1, 4 times area 2, area 3, add it up together. So what this looks like, the height would be actually this, basically the same as the length, which is, they told us it's 14 inches. So coming back down here, I got 14 inches over 6. My A1 was 2.5981, 4 times my A middle, if you will, 7.9566, plus my A3, which was what now, 16.238. That is what I wrote, right? Yep, good. That's a 3. So you end up with 118.21, and I'm multiplying inches times inches squared, I'm getting inches cubed. There's our volume, 118.21 cubic inches. So to finish the question, you always got to do that. Sometimes you get happy. You say, hey, I found the volume, cool. So, but wait, the real question is, what length of a 1" by 2" bar stock will we need in order to cast that many cubic inches of whatever this material is? Well, it's a rectangular prism, right? That's what I'm envisioning here. This 1 by 2 bar stock is going to look like a bar with dimensions 1" here, 2" here. It's going to have a certain length to it, and that indeed is the question. What length do I need here? Well, the volume of this thing is, remember, you can do like a width, height, length or something for rectangular prisms. So it's a 1" times a 2" times a whatever that length is. And I can set that equal to the 118.21 because that's what I need it to be. And so looking at this equation, 2L equals 118.21. What we got to do is we got to divide both sides by 2, and the length of bar stock that we will need is just about 59.106 inches. If you divide by 12, or if you do a conversion officially like this, 1 foot is the same as 12 inches. You can get it in feet. So the length is going to be 4.9255 feet. So I don't know if you want to go with 5 feet and have a little left over or what here. But about the calculation, the exact calculation, 4.9255 feet of this bar stock is what we would need to melt down to make this. Looks like a salt pepper shaker or something to me. Prismoidal rule, are you digging it? We can even do this with spheres, which is kind of nice. I remember struggling with a problem like this a long time ago, and I wish I had known this rule back then because it would have made my life so much easier. So you can use this whole Simpson's rule for volumes, this prismoidal rule, even on a sphere. So what do we got? 10-foot diameter spherical tank. Okay, so that means the radius of the tank is 5 feet. Okay, cool. Filled to a depth of 7 feet. Well, if it's filled to a depth of 7 feet, let's see, here's the center, right? It would be 5 feet to get up to there, right? So 7 feet would go a little bit further up. So it's filled to something like here, right, roughly speaking. So that's my 7 feet height, really, from here to here. Okay, cool. So what I'm going to end up doing is I'm going to have to figure out the cross-sectional area here, so it's going to be like a circle, right? I need the cross-sectional area here. Call it A3, I guess. I'm going to need, well, you know what? A1 is 0, right? Because at the very bottom, we don't have any. It shrinks to a point, so there's no area there, so that's actually really nice. And then A2 is going to have to be exactly halfway up, so it'd have to be at a height of 3.5 feet, I guess, right here. 3.5 feet up. So it's good to get some dimensions going, so we're going to need to know that area. Okay, now these are circles, and so the area is going to be, well, you can do pi d squared over 4, or you can do pi r squared. The trick, of course, is trying to figure out what the radius is. So let me get a different color going. How about, I'm going to go with purple. We'll go with this. So like up here, I need to know what is the radius of this circle. I'll call it r sub circle so as not to mess it up with this 5 feet, which is actually, this distance is 5 feet, right? From the center of the sphere to any point on the sphere is 5 feet. So we need the radius of the circle to get the area of the circle. We know that that's 5 feet. Hey, anyone sniffing a right triangle here? Anyone want to think SOHCAHTOA or something like that? We got a right triangle here. Do we know this side? Actually, we do, because we know it's 5 feet to get up to here, and 7 feet total means that must be 2 feet. Well, we don't even need SOHCAHTOA. We can just use Pythag theorem. Pythag would say leg squared plus leg squared equals hypotenuse squared. And if you solve that out, the radius of this circle comes out to be, well, what does it come out to be? What the heck is that? 4.58 4.5826 using 5 sig figs. This would all be feet. And so A3, I would use pi r squared here. Pi times the 4.5826 squared equals, and I think I have to hit my buttons for this one. So I got a, come on you, I got a 4.5826. I square that, and then I multiply it by the pi button, and then I get, rounding to 5 sig figs, I get 65.974. These would be square feet, because I'm using feet dimensions, right? Yeah. 65, and just kind of hang on to that. That's my A sub 3. 65.974 square feet. A2, well, I'm going to have to do a similar kind of construction down here. We'll do a green construction. I got to figure out the radius of this circle, right? There's a circle here in the cross section. And I got to figure out the radius of that circle, which would be this. R times, what do you want to circle 2? Because I'll call it R2. I don't know what else to call it. So R sub 2. And we can do that same idea that we did up here. We know that from the center of the sphere out to the edge of the sphere is always 5 feet. So that dimension's 5 feet. And I can come, well, I want to come straight up, right? Because I want this radius 2 to be measured from the center line of the sphere out to here, right? So this is a straight down. That's a 90 degrees. Can you tell me how big this side is? Well, let's see now here. It's 5 feet to get all the way to here, but this much is 3.5 feet, so that leaves 1.5 feet for right there. So that's 1.5 feet. And once more, we can do a Pythag. So where am I going to squeeze this in? A little leg squared plus this R2 squared is equal to the 5 squared. And if you do that out, you end up with, oh, where'd I put it? I guess I don't really have it. Okay, so 1.5 squared, yep. I should take basically 5 squared minus that, yep. Now I should take a square root, yep. And I'm getting that the R2 is 4.7697. And so the area then is pi r squared, pi times this 4.7697 squared, which means that I've got, okay, so square that again, yep. And then times it by the pi button. Whoa, that's the wrong button. Times the pi button, and I got that area 2 is 71.471 square feet. And of course, area 1, that was the good one. It's 0. Huh. So once you've got these 3 cross-sectional areas, the bottom, the top, and exactly the middle, halfway up, you can go get your Simpson's rule for volume. Volume is height over 6, area 1 plus 4 times area 2 plus area 3. So the height would be, we're talking about the height of our frusta, which is the 7 feet here. So 7 feet over 6. Area 1 is 0. Plus 4 times the 71.471 for area 2, plus the 65.974 for area 3. This is all feet. So we're going to get cubic feet. I'm getting 410.50 cubic feet. That is the volume of stuff in this tank. 410.5 cubic feet. Now, before we go home, we have to make sure we are answering the actual question. Let's look at the actual question again. The actual question is, estimate the number of gallons. Oh, gee. 1 gallon is 231 cubic inches. Okay? So we need to convert our cubic feet to gallons, and then we can go home. So come down to our cubic feet. Now, we know, let's go back to blue. 1 gallon equals 231 cubic inches. That's what we know. Now, you have two choices when you need to convert cubic feet into gallons. Choice number one is to stop, go get your Google out, and look up a conversion for cubic feet to gallons. I find it quicker to just do this. It's like, oh, you're telling me this? Okay, I can use that. Because I know that 1 cubic foot is 1728 cubic inches. Where the heck did I get that? Well, because if you have a foot by a foot by a foot, that's what a cubic foot is, right? It would be 12 inches this way, 12 inches this way, 12 inches this way. That's a 12. And so 12 times 12 times 12 is 1728 cubic inches. So if you have 1 foot, 1 foot, 1 foot, it's a cubic foot. It's 1728 cubic inches. You could also have just said, oh, it's 12 cubed. So I just turned my cubic feet into cubic inches, and then I can make my gallons by saying 1 gallon is 231 cubic inches, right? That crosses out the cubic inches. We got gallons. So on your calculator, you take 410.50. You multiply by 1728, and then you don't multiply. Actually, you would divide by the 231, right? And you would end up with 3070.8 gallons. That's over 3,000 gallons in there, folks. So a spherical tank which only has a diameter of 10 feet, and you've seen those around, haven't you? I've seen them around. I don't know if their diameter is exactly 10 feet, but whatever. I've seen these big spherical tanks. They hold a bunch of gallons, a whole bunch of gallons. Okay, I think we can call that a lesson. Prismoidal rule. It's one of my favorite rules. Good old Simpson for volumes.